Hello, good evening, everyone, and welcome to our very first webinar from Quantum London. So just a couple of words on who we are and what we are doing here today. So Quantum London is a community of people who are very curious about quantum technologies and quantum computing, more precisely. We hear a lot in the news about, quantum is coming, it's going to change our lives, but it's really unclear how and most importantly when this is going to happen. So we have started building a community of people who are curious about this topic and link those people with experts in the field. But what we are trying to do is do it in a non-technical way. So there are so many forums that are looking at the nitty-gritty and the details of the technology and the qubit and the physics. But we want to understand more what are the business implications of those technologies, are they going to be. So we started last year with some informal gatherings, and then in February we had our very first in-person event. Was really well attended, and we wanted to do many more of those, but then COVID kicked in, so we had to rethink ways on how to keep the conversation going and how to keep the community engaged. So we are now today experimenting for the first time with this format of webinar, and we have one speaker who many of you might recognize, Cristian Mastrodonato from Digital Catapult. He was one of the speakers in our first in-person events. And today he is going to talk to us about, I call it a reference framework for quantum computing. It's a big word, but what really we would like to get today is some anchor points which can help us understand a bit more about the technology and where it's going to go. We want to make this as much as possible as an interactive session for the community. So there is a chat functionality on the side. Please feel free to ask questions there, and we will ask those to Cristian as we go along. We will pause a couple of times to allow people to answer those questions. So, Cristian, I will let you do your own introduction. I will not take any more time here. Over to you, Cristian.
Okay, thank you. And so, nice to meet you virtually, everybody. And good evening. My name is Cristian Mastrodonato, as was mentioned. So I'm the Director of Engineering for Digital Catapult. When I mean engineering, mainly for us, it means software engineering. But I have been interested in quantum technologies. I'm interested in quantum technologies, coming from my PhD, a PhD in, I'll say foundation of quantum information applied to, non-equilibrium system, but that's a longer story. But in a way, I've always been into, statistical system and quantum technology for quite a few years, but on the other hand, I always worked more on industrial settings so far, but now eventually quantum technology is catching up and it's becoming slowly, well, not so slowly actually lately, an industrial technology, and that's why now I'm ending up also, leading the investigation of Digital Catapult on how we can, support and accelerate quantum technologies here in UK. So that's a little bit of an introduction from my side. So how do you want me to, do you want me to start, talking a little bit about the question, mention here about the reference framework, or do you have any specific question?
Yes, I think what we can structure this is we can cover the questions, and maybe at the end of each question we can pause and see if there are questions from the audience specific to those points, and then we can do a final Q&A at the end as well.
Okay, makes sense. And okay, so we'll. Sorry, I'm trying to find the best positioning for myself. And okay, so let's start from the quantum computing. I think it's a relevant element, of course, also for me, just to mention, of course, that compared to the let's say, the people, at least you remember, they attended the first, let's say, face-to-face meetup when it was still possible to have face-to-face meetup, and I gave an overall introduction of quantum technologies, and I mentioned, if people remember, quantum widgets and quantum communications, and of course quantum computing. Let's say definitely this time the idea is to focus more on one of these three, let's say, technologies, and in particular quantum computing. That's definitely because it's the main area of interest for me, and where I think also there's most potential for the future. Not that the quantum communication and quantum widgets won't have, let's say, limited impact. They will have a great impact at many levels, but definitely quantum computing can provide a sort of revolution, and that's, I think, also the point I made last time. What kind of problem quantum computing will be able to solve? I think it's important, again, to make one, let's say, one step back, and I appreciate sometimes, let's say, it's complicated in a way to introduce quantum computing without mentioning, let's say, phenomenon like superposition and entanglement, but without, let's say, taking time explaining what they are, because of course that would become quite easy a sort of introduction to, let's say, to physics or quantum physics. I think the main point of quantum system, and in the way we should see them as computing system, is that they are, let's say, from a point, let's say, the ultimately parallelized system. Okay, so if you think to the typical digital way of approaching operations is let's say is a serial way. Okay, so we have CPUs and GPUs, but basically a processing unit in a digital let's say system is basically processing instruction one at a time. And then of course you can try to parallelize it as trying to have as many CPU as possible, or GPUs, or processing units in general. But at the end, it's limited by the number of, let's say, cores you are, as they say, but if you heard, let's say, and especially if you are into machine learning and artificial intelligence, the real thing is that most of the optimization problems on the other end to be solved and I'm using optimization here probably in a quite of improper and very generic way. I will try to be a little bit more precise, let's say, in a few minutes. But any sort of optimization problem, let's say, it needs a hugely parallelized approach. Okay, and that's where basically there is definitely this limitation. And if you think about that, if you all of us already know and highly parallelized machine, okay, and highly parallelized optimization and predictor machine, and it is our brains. Okay, so our brains work very well exactly because their single processing unit, the neurons, are sort of are not very much power. They consume very, let's say, they're not measuring megahertz, and they're processing, let's say, the power they need, it is very limited. But the value we have is that they are, I don't remember the exact number, probably we're talking of multiple of billions, probably, I don't remember if million or billions, trillions, or something like that. Sorry if I don't remember this number, but you got the point. It's definitely a number which is way more than this processing unit we are usually to work. That's our brain works, and that's the difference. Okay, so definitely there's one element that if we want to make the next step in machine learning and artificial intelligence, let's say quantum system on the other hand are highly parallelized, and the reason is because each processing unit, in a way you could call it, or each piece of information, which is the quantum dot, can be connected with the others, and that basically allows to compute all the different possibilities at the same time, and let's say spit out as an output, let's say, the probabilities of having all these different, let's say, these different options. And if you think about that, like, it works the other way around of the typical, let's say, training system that we have, okay, where it takes a lot of time to process, possibly in parallel, let's say, many different models and trying to find the best optimization problem. But naturally, a quantum network can sort of, let's say, a network of quantum dots can naturally, let's say, parallelize the solution, because that's really how, let's say, the quantum physics behind that process it. Okay, so it's really kind of changing the paradigm from a linear paradigm, a serial paradigm, because that's the, let's say, the von Neumann architecture, which is derivation of the Turing architecture, basically with stuff that came up during the, let's say, let's say around the Second World War, if you think about that, so 70 years ago, stuff like that. We're still using the same architecture there. And let's say with the quantum computing is a completely way to implement the computing architecture. That's really the difference. So in a kind of, let's say, that it was a nice way to naturally introduce, of course, the area where the quantum computers can be good at. Okay, so there is an area of I mentioned, let's say, optimization problem and forecast problems, which often are kind of, let's say, there are similarities among the two without going too much into detail. There are, let's say, of course, sort of unstructured search problem, which are related again, because you are, let's say, exploring into in some cases a high dimensional space, if not the infinite dimensional space. And again, a quantum space is naturally, let's say, multidimensional, if not tend to be infinite dimensional quite easily. And again, so these are natural ways. Okay, so again, in a way, what you do here, you change the architecture of the computation to solve, let's say, reality problem. And somehow the lowest hanging fruit is quantum chemistry. Okay, so quantum chemistry is a field that has been tackled from quite a few years now. I remember when I was a PhD student, to be fair, I had the opportunity at the time. I didn't follow it up to work on quantum chemistry, which is basically simulation of quantum system. I did a little bit of simulation of quantum system, but the interesting bit was we're talking of more than 10 years ago, and quantum computers weren't a thing. Well, were a thing, but a more theoretical thing than a real thing as they are now. Is like the real point is that if you with chemistry where we are now and the understanding of materials, again, using normal standard digital computers, there are limitations again on understanding the complexity of the system. Again, because you end up having to simulate complex behavior of molecules, which are natural statistical, and again tend to be infinite dimensional problem or very high dimensional problem. And there was a nice, I cannot quote exactly, but there was a nice point of Feynman, let's say, which probably, let's say, Nobel Prize for physics, and one of the inventor of, the person that came up with quantum electrodynamics, which is basically the basic of modern, I would say, field theory, which is good part of quantum mechanics in the end. What he came up to the point that if we really want to understand reality, we need to simulate with tools that resemble reality, and reality is a quantum reality. Okay, and that's what we have to accept. So especially when you go to chemistry and the behavior of let's say, molecular behaviors, molecules behave in a quantum way. So the best way to simulate that behavior is with a quantum computer, not with, let's say, digital computer, because with the digital computer, the only thing you can do is to try to simulate in a way and emulate within certain, let's say, within certain limits, but very, very big limits, the behavior of a quantum system, and trying to break out into a digital way. And again, with a quantum computer, that it's different, because you kind of map a quantum problem into, let's say, the molecular space, into a quantum problem onto your quantum computer, and that makes, let's say, it's going to make a lot of change. So this is going to have, of course, and if you think about, and I'm stressing a little bit more about quantum chemistry, because a lot of the problems we have around us nowadays, we are talking of drug discovery, and of course we are in the middle of pandemic, and that's a good example. Of course, I mean, we're talking of vaccine and drug discovery and finding quickly new drugs. So definitely there is many pharma companies are going to move there, and so there is a discussion about industries. There's just a second question, and I'm going naturally into there, but then it's the development of new materials is going to have a lot of impact into, for example, well, anywhere, again, into the climate change. Think about developing new materials for batteries, developing new material for carbon captures. We really need to get close to the limit of what materials can do, and you can only do it using quantum, let's say, computing, possibly, or definitely we are very close to, let's say, the only thing that limits us in a way at the moment is the Moore law on the digital side, and but the reality is to get to the point where we want to get at the level of simulation that we need to get, it might take, if we just follow the Moore law trend on the digital, it might take 30, 50 years, while the leap we can do with quantum computing, it might be these sort of simulations and in general, let's say, exploration of quantum chemistry can be done, let's say, in a 5 to 10 years time frame. So it's a radical reduction of time and acceleration of what we can get there. So I think these are the main, let's say, kind of problems. I mentioned a few industries. So of course, as I said, the quantum chemistry is probably one of the area with a sort of shortest term application, again, for the reason I mentioned, which is about kind of, again, simulating quantum system in a way. And the best way to simulate a quantum system is a quantum computer. There are other elements, again, which complex parallelized, let's say, calculation around, let's say, aerodynamics, probably. So probably aerospace is going to be another industry which might have a little bit lower hanging fruit, and there are already companies like Airbus and Boeing investing heavily on these technologies, because I mean the mindset is when quantum tech will pick up, it will disrupt completely. Okay, so the company that won't be able to jump on that train, understanding it, they might disappear in the matter of let's say literally a few years, because the technology advantage that you get in some specific areas, adopting such high level of parallelization is, let's say, is huge. Jumped into optimizations problem. Of course, here it's probably problems which are more related to the, let's say, maybe, let's say, at least part of this audience. I remember, and I'm assuming, of course, this audience similar to, say, the one last time, so closer, of course, to the insurance industry, like Em and Paolo are coming from. So, of course, there are a lot of optimization problems to be solved, and of course, so I think the easiest way to see it from the point of view of banking, insuring, let's say, insurance and finance industry is a sort of extension of artificial intelligence. I think that's the artificial intelligence fields. That's, I think, is the easiest way to see the extension, let's say, the direction that quantum computing is going to get. But again, in some specific areas, there might be completely, is going to open up a completely different world, because again, thinking about extreme parallelization, okay, beyond anything that has been done so far, it means, of course, that you can manage to simulate very and model and optimize very complex environments. Going again a little bit outside maybe the finance, insurance, banking industry, another area that sounds interesting, for example, is around smart cities. If you think about that, because of course, again, cities and in general simulation of let's say, it's not necessarily only about traffic, but in general of a complex, let's say, social environment with many agents, let's say, behaving and interacting. This is again a highly parallelized problem that can be tackled with, let's say, with quantum computing. So definitely there is an area about, let's say, smart infrastructure, smart systems. So going to the status of the market.
Before,
I see.
Sorry to interrupt you there. So there are a few questions in the chat in the meantime, and one I wanted to ask before we jump into the third part. Obviously, our circumstances, the whole situation with COVID and social distancing, the question came out naturally in the chat. Is this an area where quantum computing can potentially help or not?
Let's be realistic. No, on the time frame that pandemic, I mean the current pandemic where we are now, you need answer within 1 year, and no. It might help since many are predicting this is going to be the first of the others, it might help in the future though, in the next one. Hopefully is going to be, let's say, sometime in the future. But again, following the prediction and let's say other sort of inputs that are, I mean, assuming, and hopefully they're wrong, but assuming those, let's say, prediction are correct and new pandemics might happen in a near future, that might help. So that's where it's more than might be the 5-year time frame we could expect contribution from.
And which are the areas within the pandemic that you think quantum could contribute the most? Is it, for example, in the DNA discovery and I think building a vaccine, or is it in the simulation of the?
It's not. I know. Okay, I never heard about you. Okay, DNA is tricky. I never heard of that. It doesn't mean it's not possible. Okay, it's my limited knowledge. Okay, so when it comes to chemistry, again, the problem number one you have to solve when you build a new drug is that the new drug is going to attach on something. Okay, usually it is going to attach to the virus, for example, to prevent. So the new drug is a molecule which is going to attach to the virus, for example, or the bacteria, whatever is the disease, and it will try to modify the behavior of this virus. For example, typical situation is I hinder the capacity of the virus to attach to cells of my body. Okay, because let's say these molecules, this drug, it's gonna let's say prevent the virus to attach to part of the body. I'm oversimplifying it. Okay, very, very, very much. But the problem is we are talking of interaction at molecular level. Okay, so usually, for example, you saw the coronavirus by the name. They have all these little spikes. Each of these spikes are a bunch of molecules. Okay, even are not really spikes, are, let's say, columns of molecules, and you need another, let's say, thing, it's actually substrate usually that attach to that, let's say, spike to prevent it attaching to something else. That's more or less, for example, in the case of coronavirus. So that kind of understanding was the right shape on, let's say, the drug, the molecule you're developing that attaches on the spikes, for example, the coronavirus. And again, I'm oversimplifying, and I'm sure anybody expert in chemistry here might want to kill me, and with, let's say, and I would probably deserve it. Is the mindset is it's a very complex problem from a, let's say, a simulation point of view. What's the right shape of the molecule? I mean, you cannot just say, oh, that's more or less like that, because just slight variation in the electromagnetic fields generated by the molecule might change an attraction to a, let's say, behavior, to a rejection behavior. Okay, so a repulsion behavior. So it's complicated in a way. What you want is creating a binding. Okay, and the reality is that the geometry of, especially of proteins, is very complex. So the same configuration of molecules can create, with the very same number of atoms, can create completely different geometries depending by the way they are built. And that's, again, is basic of quantum simulation. So that's really where I believe is going to be the main advantage. So when it comes to DNA, there are geometric problems also with DNA. DNA are proteins, and you want to, for example, in specific ways, you want to, let's say, disassemble them and assemble them in different way. So there might be application there. I don't know, but the typical problem of drug attaching to some substrate to, let's say, prevent or make things happen, that's the basic dynamic that needs quantum chemistry, and that's where quantum computing is going to help a lot.
Should we move back to the agenda then?
Okay, so I think I more or less covered the first two questions. So I can go to the status of the market. So status of the market, that didn't change much, of course, from our last discussion. Of course, we are talking of a highly. This is still an R&D phase. Okay, so commercial applications are not close, but I think we can roughly split up the status into 3 layers. Okay, and yeah, I think at least that's the easiest way I explain it to myself. So I'm going to share with others. So there is the computing layer, which is very complex, which is about quantum dots. How do you build a computer? Okay, so how it is build your quantum dots, and people for sure heard of different technologies. The most famous is superconducting technology, where let's say Google is moving, D-Wave is moving, IBM, Rigetti, all those names. Then there is a new technology where probably, by the way, your case is also has still a competitive advantage. It's about trapped ions. And then there are other technologies around photonics, neutral atoms, silicon, actually. Silicon quantum dots, and Intel is mainly working on that, for example. And other technologies a little bit more esoteric, which I like topological dots, but that stuff, for example, Microsoft is spending quite some efforts in there. But I think, I mean, in a way, it's really about the processing unit and how they connect it together. Okay, how do you build the quantum computer? That's really where most of the research, not all, but most of the research is focused there. Each of them, they have pros and cons, and I invite you maybe, I mean, that might be a wider discussion. So, okay, if there is a specific question, I might get back, but yeah, it can take some time to differentiate between the different technologies. So that's the basic layer. And there are some similarities to the typical, how you say, digital computing. When you go to the basic layer, there is an interesting element there. There are efforts, and many are already doing, kind of everybody building supercomputer, are also building emulators of those quantum computer. And the reason is because until a certain limit of quantum dots, I don't remember the exact number, but it's something like 24, 20, 24. I mean, a quantum computer can even run on your laptop. Okay, so in emulating a quantum computer, it runs on your laptop. It's not that complicated. Until you go over a certain threshold, you cannot even emulate it into the fastest supercomputer. And it's really literally, I don't know, I'm making up numbers here. Apologies, because I don't remember exactly. But it's something like, I'm pretty sure that I've said 24, it can run on your laptop. I'm pretty sure 48. Probably you need to run, it can barely run on the fastest supercomputer in the world. And I just doubled the number, but that just gives you an idea, okay? And if you want to go to get to 96, that's absolutely impossible to build. So these are just to give you, again, a rough scale, okay? I might be wrong on the 24, 48, I'm sure the 96, but if it's not 48, it's 52. So it's just to, I mean, these are the numbers we're talking about. So you want to emulate them, because of course, that's the easiest way and the less expensive way to test the software. Okay, so in a way, the software is the interesting bit. Okay, so that's where a lot of research is going on in parallel, because the software is what is going to make, let's say, run your quantum chemistry or your optimization algorithm. Because it's like if it's not the easiest way to explain, again, if it's incorrect within certain limit, is like we are learning how to write in a new programming language that nobody used before, and nobody has an idea what you can do with that. So that's more or less where we are. Okay, so the reality is that we know we know the basic element of this programming language, which are the quantum gates, and you can combine them in different ways. There are limitations also due to the underlying hardware architecture, how you can combine the different gates. But the mindset is, when you build the geometry, you build different quantum gates together, things are going to happen. That's more or less the way when you write this software. And we still don't know which algorithm are going to run. So there is a lot of work going on now on creating new algorithms and testing them, because some of them are not going to lead anywhere. Most of them probably, actually, let's say not probably, very likely, but some of them are going to be very powerful. And there is a lot of, but again, without quantum computer, you don't really know. And of course, the geometry, the bigger is your quantum computer, the more complicated and potentially powerful algorithm will come up. So that's where there is a lot of discussion there. And that's really where, I mean, you can have a great quantum computer, but if you don't have the right software running on it, if you think about it, it's obvious, but it applies more or less in the same way. But really think, but the way you need to think is really like when we were talking of algorithm running on the very first computer just after the Second World War, and nobody really knew what they could do with a digital computer. That's more or less the same thing. Okay, so most of the algorithm now we give for granted. 60 years ago, they didn't exist. Nobody knew. That's more or less where we are. Then there is an interesting layer which sits in the middle, which is what I would, conversation, having with colleagues of mine, let me say, working on a quantum bit, which what we would call, and others are calling, the operating system. So can I build an agnostic way where whatever algorithm I'm going to write, this is going to run on the Google quantum computer and the IBM quantum computer and the Rigetti quantum computer and the Intel one? That is going to be an interesting level, okay? Because at the moment, those hardware are incredibly specialized, proprietary, and an algorithm working on one might not work and very likely won't work on the other for a lot of reasons, given in particular geometrical limitation of the dot network and in the way it is built. But it could be also, let's say, regarding, let's say, the coherence time. That there are a lot of course, there are a lot of limitations, especially now on a quantum computer.
Can we jump in on,
yes.
on that question? Because I think that's a very important one that's come up. So essentially, companies are going to have to take a bet on which technology and therefore which of the major suppliers they're working with because of this fact they're so fundamentally different? Or do you think that there will be emulation layers, which mean that if someone spends the next 3 years working with one company, but then another one builds a significantly stronger machine, they can just flip over?
I think, I want to, it's important we make a distinction between the emulation and what I call the operating system. So the emulation per se emulate one specific kind of architecture. So I can emulate the IBM computer and I can emulate the Google one, are two different systems. Okay, so that's what the emulation behaves. The operating system is a sort of translation layer. It's exactly how an operating system runs now. Okay, so when if you think about that, I don't really care what motherboard or what CPU or GPU I'm running in my laptop. I know my Windows works, more or less. Let's say blue screens apart, let's say aside, it works, okay? And that's more or less, so that's where I'm talking the operating system layer. So I think, said that, to answer to your question more directly, I think at the beginning, there is going to be that sort of dynamic similar to the digital world. If you remember, there's been a lot of discussion over the years between vendor lock-in. At the end, if you remember, if you bought an IBM, it was running on an IBM. If you bought a Mac, it was running on a Mac, which is, by the way, still the same now, but that's probably another story. But let's say everybody else kind of converged. So we have Mac and non-Mac probably, kinda, and even there probably the underlying hardware is also converging now because they are everything using an Intel architecture. And so you got the point. So I think there is an element there where probably at the beginning they will try to do some vendor lock-in. And for the most advanced algorithms, yes, you might have algorithms run only on top of a single architecture, because that's where they will want to differentiate. But already now you can see, for example, there is actually a startup here in UK which is called Riverlane. They trying to build this operating system layer already. So very likely what is going to happen is that probably you're going to have kind of two tiers of algorithms that can run on most of the platform, let's say maybe simpler, but most accessible for many of the applications, and very, very, very narrow algorithm that can run only on specific, let's say, solutions. But then more or less also how the market is now, if you think about that, okay? If I want to run, there are machine learning algorithms run on specific GPU farms designed in a certain way.
So that's
like something like
that makes sense. And your mention of a UK startup is maybe a nice segue into that question. So yeah, there's large players investing in this, and there's a number of startups. Where are they getting money from? Be good if you could talk us through whether it's government money, VC money, large potential customers, where they're being sourced.
I think well, the easy answer is all the three of them. Clearly, if you look, okay, so the wider landscape is that there are big government investment on fundamental R&D, on foundational R&D. There are large private investment on applied R&D, and I think about IBM and Google, which are pushing the boundaries, okay? So they're taking what is coming from university and really pushing it closer to the industry. And there is a lot of VC investment around a lot of startups, okay? So in that sense, that's more or less the way it splits. Now, and there is a lot of movement, and there was a nice report. I mentioned it. I don't remember. I think I mentioned when we did, let's say, the meetup last time. There is a report from Nature, which is almost now 9 months old. It compared, I think, was 2015, 2016 against 2017, 18, and the investment quadrupled. Was 4 times. Let's say on a 2-year time frame to the other 2 years. Probably here, at least it was another 4 times, if not more. So if you think about that, that's an exponential low, at this case, also in the investment in the sector. Okay, so that tells a lot, because clearly quantum computing is coming, and there is a lot of investment there. But
to be doing it.
Sorry.
So is the UK, if I wanted to push this as an investor or as a tech startup, should I be here or should I go somewhere else?
I think if as is a tech startup, it's very convenient for you. I mean, UK is a great place because there are, among the best universities. Most of the research is happening here. Okay, in other countries, but let's say definitely at research level, it's top notch, and a lot of startups are coming out of here. And the government is also helping. The issue, in a way, is that most of the private funding is coming from outside, though. So there have been, I didn't make the math, I'm sorry, but I've seen a few investment of 200 millions of that size here in UK, but all the money were coming from US. Okay, so just to say, so we're talking of even a pretty decent and good investment, but not from the inside, from the outside. So in a way, it's a pity because it was research coming up funded by UK taxpayers, but let's say then the industrial takeoff, let's say the industrial take on is, let's say, an industrial investment is more coming from the outside. That's the scenario we're seeing now. We are in the middle of doing a little bit of a landscape also in Digital Catapult. So situation, we might be able to provide a little bit more updated information, we'll say summertime, but that's where we are. That's the impression we have.
That's helpful. So there were a number of questions that came in, and I'm aware we're just a few minutes from the end. So I wondered if I could just raise those from you. So one was, there's clearly a lot of potential power in quantum computing done correctly. Does that mean that it needs to be managed and overseen by government rather than being left to individual corporations?
I mean, it's a good question, which is in a way inherently political, let me say in this way. So it depends also what you believe. So I mean, that's really my personal opinion. I think so. On the other end, if I look around, and maybe with the pandemic, the situation changed. You saw the amount of money that, for example, all the governments are putting into protecting the economy and stuff like that. I mean, but you also see the level of investment that private companies are putting. So the government should chip in, yes, but would the taxpayer accept 20 billion investment or 50 billion? Because these are the money that Google, IBM are pouring into that. Okay, so would the taxpayer accept those money spent? Which is a little bit similar, again, into, let's say, would they accept those money spent in healthcare? But that's a little bit the thing. If you ask me, probably the countries should. Probably it's easier to influence through regulations in some way. But yes, it's really powerful, and potentially, like nuclear technology, if you think about that, it can be used in good ways and bad ways.
Good, thank you. And then there was a question around if people are interested in this, and they don't want to become research scientists or whatever it may be, but if they're interested, what should they be doing as individuals to make sure they have the right skills to exploit this over the years ahead?
I think there are quite a few outlets like this one, for example, to be fair, that can help them stay up to date on what's going on. And I think that's the suggestion. If they want to play a bit, I'm the only one I'm familiar with. There might be others. I mean, I also suggest them to have a look to the different quantum projects. For example, the IBM Q, which for other reasons I'm not super fan, because basically their licensing is very closed and I don't necessarily like it, but they have a very nice graphical user interface to simulate quantum systems. So you can make drag and drop a very basic quantum circuit and see what happens. So if you want to go one level beyond and play a little bit with that and understand what we are actually talking about, for example, and I think there are others building similar interfaces. I think Microsoft as well. So you can check out. I know better than IBM Q because it was my first approach, at least personally, a few years ago. So you can also go to that level and play a little bit with the simulator, because I think the issue with quantum technology is that is counterintuitive for the human brain. And the things that happen, you don't really expect them to happen. You would have to expect the other way around. So having a basic understanding helps you in a way also accept that the way this technology, let's say, is sort of taking off at the moment. You're muted, or I don't hear you.
Good, thank you. The final question is almost inevitably, again, going back to one you touched on earlier about the question of when. So yeah, in some very, very narrow areas, it's already starting to be impactful. But as we look around, those of us working in traditional industries, in middle management jobs, will this really be important to us in 2 years, 3 years, 5 years? And will we be a
I
big
think
bang?
it's difficult. Okay, these kind of predictions are always going to be, let's say, difficult to make, especially because this is the comment I have is, until a few months ago, I was like 5 years to have a industrial ready, let's say, intermediate noise reduction quantum computer. I think I used it the right term. Sorry that and that's where I think, and 10 years to have sort of more, let's say, kind of complete quantum computers. But to be fair, over the last months, I've seen things accelerating too much that I'm started thinking that we might have the first industrial application even in 3 years' time. But I would say 3 to 5 years, I would expect actual application happening. Let's say the complete, let's say, adoption is more on the 10 years time frame.
So that's been really helpful. Are there any final passing thoughts from you that you want to just give to the audience?
I think, I think all the questions were really brilliant. The only comment I have, again, and probably the knowledge I gave at the beginning of having a sort of super AI in mind, not from the point of view of let's say technological singularity, but having a sort of disruption in the way AI works I think is the best way, especially in the finance/insurance let's say industry. And but I stress the point I made latest, which is this is an exponential technologies and it's taking off. And I can see that right in front of me. Every prediction on a bunch of things on a short term I made, it took, let's say, 1/3 of the time I expected, or 1/4. So I was expecting next year, and I have already solutions in front of me. Okay, that's more or less where. So it's like, and on the other end, it's a technology that when it's in your hand, it can disrupt everybody else. So it's good to have a look, understand what it is, and trying to spend, if you have an innovation department, or start investing a little bit some time, having a few developers. You can now program quantum computer using standard programming languages, okay? So something you can do already now. So maybe having people starting looking at it, playing a little bit, start building that capability inside your company is something that it's better to be done sooner rather than later.
Brilliant. Okay, Christian, fantastic. Thank you so much for the clarity and for answering those questions. We really appreciate you being part of this community and look forward to an ongoing conversation with you. So I'd just like to wrap up by saying thank you to everyone who joined us, both those who joined us live and those who are listening to this as a recording. Hopefully you found this webinar interesting. As Em said at the start, our aim is to look at the what and the when of quantum technology, but from a business point of view. So, a discussion that could be had in an ordinary company about the implications for that company. So I'm sure you'll agree that Christian has done a good job of that. So thank you. And, we look forward to many similar conversations. We'll be doing events like this over the days and weeks ahead, digging into specific elements of this reference framework in more detail. So please follow us on LinkedIn, on Meetup, or on Twitter. And if there's anyone in particular you'd like to hear from, do let us know and we'll see if we can get them to join. So thank you. Good night.
Thanks a lot. Thanks, everybody.